Alright, in this video we're going to solve simultaneous equations using matrices. The method we're going to use is by pre-multiplying the matrix of constants by the inverse of the matrix of coefficients of the simultaneous equations. And if you don't know what that means, don't worry, because you soon will. So let's have a look. So say we've got simultaneous equations 2x plus 2y plus 3z equals 26, and 4 lots of x minus 1 lot of y plus 2z equals 11, and 3x plus 3y plus 1 lot of z equals 25. So the coefficients are like the 2's, 3's, 4's and minus 1's. The variables are the x, y and z, and the constants, if you like, are 26, 11 and 25. Now we actually did this same example using the Gaussian elimination method on my other video. I'm doing this after that, so I know what values of x, y and z are going to pop up at the end. X is going to be 2, y will be 5 and z will be 4. But I just want to do it to prove that it works this way as well as the other way. So here is the matrix A, which is the matrix of coefficients, and they are the coefficients of x, y and z, as in the numbers that we multiply x, y and z by in the three equations. We have x, which is like the matrix of unknowns, the actual values of x, y and z, the variables, and B is the matrix of constants, which is like the numbers at the end, like the answers to the equations. But really our answers are going to be the values of x, y and z. We want to find out what they are using this method. And if you're wondering where it comes from, the equations are in the form a times x equals b, as in something times x, y and z equals a number. So a times x equals b. If we multiply both sides of the equation by the inverse of a, on the left hand side we have the inverse of a times x is equal to the inverse of a times b. But it can be shown that the inverse of a matrix, say the inverse of a times the matrix itself, actually becomes the identity matrix I. So a to the minus 1, as in the inverse of a, times a itself equals the identity matrix. It can also be shown that the identity matrix times matrix x is just matrix x, because when you multiply a matrix by the identity matrix, it doesn't change it. So now we've got it in a nice form to find our matrix of variables, the unknowns x, y and z. It's just the inverse of matrix A times matrix B. So matrix A times matrix X equals matrix B. We want to know what matrix X is. It contains three variables, X, Y and Z. We want to know what their values are. So there's two steps. Step one is find the inverse of matrix A, the inverse of the matrix of coefficients of X, Y and Z. Then pre-multiply B by the inverse of A. So that just means get the inverse of matrix A and multiply it by B in that order. And the answer, because we've got a 3 by 3 matrix times a 3 by 1, the outer dimensions are going to be a 3 by 1, so it's going to be a 3 row, 1 column matrix. That's what X is going to be. So in order to find the inverse of matrix A, if you don't know how to find the inverse of a matrix, you need to watch the other video that I've done on inverting matrices, finding their inverse. I'll assume that you've watched that, and we'll go through the process now. The first thing we need to do is find the determinant of matrix A. So the determinant of matrix A, also known as like the A with these vertical bars, is equal to the first element times the mini determinant of what's left when you ignore its row and column. So that's minus 1 times 1, take away 3 times 2. I'm using this dot operator, so that's equal to 2 lots of minus 1 minus 6, which is 2 lots of minus 7, which is equal to minus 14. The second number of the determinant is, it would be 2 times the mini determinant of what's left, but because every other element needs to have its sign inverted, it's going to be minus 2 lots of 4 times 1 take away 3 times 2, which is equal to minus 2 lots of 4 take away 6, which is equal to minus 2 lots of minus 2, which is equal to 4. The third number of our determinant is going to correspond to the first row, the third element, which is 3. So it's going to be 3 lots of the mini determinant of what's left when you ignore 3's row and column, which is 4 times 3 take away 3 times minus 1, which is equal to 3 lots of 12 take away minus 3, which is equal to 3 lots of 12 plus 3, which is 15, which is equal to 45. So the determinant of A is equal to minus 14 plus 4, which is minus 10, plus 45, which is equal to positive 35. So that is the determinant of A. So the cofactor of the first element, the cofactor of element 2, gives us minus 1 times 1 take away 3 times 2. So we've kind of already done this nearly. So that's going to be minus 1 take away 6, which is 7. So that is the first cofactor. The cofactor of the second element, which is also happens to be 2, is going to be 4 lots of 1 take away 3 lots of 2, which is equal to 4 take away 6, which is equal to minus 2. But because every other element, its cofactor needs to have the sign changed. If it's plus, make it a minus. If it's minus, make it a plus. Starting with the second one, the cofactor for element 2, we need to change this sign into a positive sign. So it's actually going to be plus 2, which we just write as 2. Element 3 gives us 4 lots of 3 take away 3 lots of minus 1, which is equal to 12 take away minus 3, which equals 12 plus 3, which is 15. So that's the cofactor for element 3. Element 4 is going to give us 2 lots of 1 take away 3 lots of 3, which is equal to 2 take away 9, which is equal to minus 7. But because this is one of the every other numbers, we need to change the sign of this. So the cofactor of 4 is actually positive or plus 7. Element minus 1, which is the second row, second column, is going to give us 2 lots of 1 take away 3 lots of 3, which is equal to 2 take away 9, which is equal to minus 7. And we don't need to change the sign of that one. It's only every other number. Second row, third column, the element with the value of 2 is going to give us 2 times 3 take away 3 times 2, which is equal to 6 take away 6, which is equal to 0. And you don't need to change the sign of 0 because it's just 0 anyway. We would have had to though if it wasn't 0. Bottom row, first column, element 3 is going to give us 2 times 2 take away minus 1 times 3, which is equal to 4 take away minus 3, which is equal to 4 plus 3, which is equal to 7. Third row, second column is also a 3, and its cofactor is going to be 2 lots of 2 take away 4 lots of 3, which is equal to 4 take away 12, which is equal to minus 8. But because it's one of the ones we need to change the sign of, the actual cofactor is going to be plus 8 or positive 8. And finally, third row, third column, the cofactor of this little element 1, 2 times minus 1 take away 4 times 2, which is equal to minus 2 take away 8, which is actually minus 10. So that's all the cofactors. So we're getting somewhere. Now we're going to write them into a little matrix called the matrix of cofactors. And spot the deliberate mistake. Minus 1 take away minus 6 is actually minus 7. So it's always worth pointing out that you have to be careful with your negative numbers. So I've just plugged those numbers into a matrix of cofactors. We usually call it C. And to find the adjugate, which is part of the inverse, we need to transpose the matrix of cofactors. So you make each row a column, or make each column a row. It's the same thing. So I'm going to make the first row a column. So minus 7, 2, 15. Then I'm going to make the second row the second column, which is 7, minus 7, 0. Then I'm going to make the third row the third column, which is 7, 8, minus 10. That is equal to the adjugate of matrix A, which is our original matrix. Now if you've watched the video on making inverses, to find the inverse we need to divide the adjugate, which is the transpose of the matrix of cofactors. We need to divide it by the determinant, or multiply it by 1 over the determinant. So a to the minus 1 is 1 over the determinant of A times the adjugate. And we know what the determinant is. It's 35. So the inverse of A is 1/35 of the adjugate. And this is like a scalar multiplier, even though it's a fraction. So a to the minus 1. Let's draw the matrix box, make it big enough because it's going to have a load of fractions in. Divide everything in the adjugate by 35. Minus 7 over 35, 7 over 35, and 7 over 35. Second row is 2 over 35, minus 7 over 35, and 8 over 35. Third row is 15 over 35, 0, and minus 10 over 35. So now all we have to do is multiply the inverse of A, which we've just found, by the matrix of constants B. And because this is a 3 by 3 matrix and this is a 3 by 1, the inner dimensions match, so we can do it, and the answer is going to be a 3 row by 1 column, which is what we expected for the matrix of unknowns, the matrix of variables, which we called X. So let's multiply them then. The top row by the first column will give us the top variable, as in X. So what that is minus 7/35 times 26 added to 7/35 times 11, which is 7 times 11/35, and add 7/35 times 25, or 7 times 25 over 35. Second row gives us 2 over 35 times 26, is 2 times 26 over 35, doesn't matter which way you write it. And we've got minus 7/35 times 11, so it's minus 7 times 11 over 35, plus 8 over 35 times 25. You could write it as 8 over 35 times 25 if you want, that's fine. Bottom row, 15 over 35 times 26, plus 0 lots of 11, minus 10/35 times 25. So clean that up a bit. Minus 7 times 26, or 7 2s are 14, so 7 20s are 140, 7 6s are 42. That's minus 182 over 35, plus 77 over 35, plus 7 25s, or 4 25s is 100, so that's 175 over 35. Because they've all got the same denominator, they're easy to add. 182 plus 77, that's 105, but it's minus 105. Minus 105 plus 175 is 70, so that is equal to 70 over 35, and that is equal to variable x, and 70/35 are 2. So x equals 2, or 2 equals x, the same thing. We've solved x, which is one of the things we needed to do, so x equals 2. Now to solve for y, 2 times 26 over 35, 2 26 over 35 is 52 over 35, minus 7 times 11, minus 77 over 35, plus 8 lots of 25 is 200 over 35. 52 minus 77 is like 77 minus 52 with a negative sign, so that's minus 25 plus 200, so that's positive 175 over 35. The 35 goes into 175 5 times, because 5 30s are 150 and 5 5s are 25. So that is equal to 5, which is equal to y. So we've solved y. So y equals 5. Last but not least, 15 times 26, well that's 260 plus half again, 390 over 35 plus 0, minus 10 lots of 25, so minus 250 over 35. Well, 390 minus 250 is 140, and the denominator is 35. And that goes exactly 4 times, because 4 30s are 120, 4 5s are 20, 120 and 20 is 140, so that is equal to 4, which is equal to z. So we were now solving for z, and we've got that. So z equals 4, which is exactly what we were expecting, and that was the same answer as we got using row operations and Gaussian elimination method. So happy days. So that's how you do them. Any questions or comments, please leave them below and I'll be happy to let you know. Alright, thanks for watching. Cheers.